All right. So yesterday, in last class, we talked about chemical reactions. Okay, and we learned a few important things. First, let me go back a little bit. We learned that in a chemical reaction, a sign of that happening, so you mix two chemicals together and it feels hot or cold. A change in temperature is a sign of a chemical reaction. Seeing light is also a sign of a chemical reaction. This is pretty rare, but I mean, when you burn a candle, that's a chemical reaction. In the lab, we mixed sodium and water and we saw little sparks of light. That's a chemical reaction. Oops. Seeing new color forming would be a chemical reaction. So you mix, two clear colorless solutions and it turns white or blue or yellow. That's a chemical reaction. A solid is formed. So you mix two liquids together and you get a precipitate. Um, that's a sign of a chemical reaction. And a new gas being formed. So typically you'll mix chemicals together and you see bubbles. That's a sign of a chemical reaction. So all of these things are signs of chemical reactions. Then we learn, I'm going quick through that, guys, because we did that yesterday. So if you weren't here yesterday, just go back and watch one of the old videos. Um, other things we learned are the major components of a chemical reaction. We have the reactants on the left, the products on the right, and then in the middle, we have the arrow that separates them. Just remember, and I'm going to get into the new stuff in the next minute or so, but just remember that the reactants are like your ingredients in a recipe. And I mentioned the analogy yesterday of like baking a cake. If you're baking a cake, you have ingredients, flour, sugar, eggs, butter, things like that. Those are the reactants. And then you would separate that with an arrow and the product would be like, a cake. Or in this case, we have sodium and chlorine. They react together to produce sodium chloride. Okay. And we did this question yesterday. So here is the new stuff. States of matter. There are two components left for a good chemical reaction. What I mean is for properly writing a chemical reaction. The first component that I have to cover is the states of matter or phases. What I mean by this is when you write a chemical reaction, you also want to tell the person if you say you're writing a chemical reaction for me or for another instructor, you want to tell us if the chemicals are solid, if they're liquid, if they're gas, or if they're aqueous. And aqueous is kind of a new concept we learned about in chapter 4. Aqueous is the most common. In CH1120. I'm not saying it's the most common in nature, not by any stretch. I just mean in, a first year chemistry course, we're typically looking at aqueous solutions. The reason we use aqueous solutions is because ionic compounds are often in the lab found as solutions. They're dissolved in water to help make a reaction happen faster. Like, just imagine first understand what a reaction is. A reaction is when the molecules bump into each other. They literally have to touch each other. I say molecules, I mean atoms or ions, and they need to form something new. The only way that happens is for them to bump into each other. So just imagine trying to mix two solids together versus two liquids. In liquids, the molecules can move and flow and spread around, and it makes them a lot easier to bump into each other. So long story short, you do see aqueous a lot in the lab. Some of you might be wondering, what's the difference between liquid and aqueous? Liquid is when it's a pure substance. So for example, like pure H2O or pure mercury. I'll explain why mercury is a liquid in a minute. They would be liquids. They're not aqueous. Aqueous means that the chemical had to be dissolved in water. So pure H2O is not dissolved in water. It is water. And pure mercury is just liquefied metal. So how do we know if it's a solid, liquid, gas, or aqueous? We use the data book, right? How many times have I talked about the data book this year? So many. So your data booklet has two very important pieces of information for the states of matter. For elements, we would use the periodic table, right, in the data booklet. The periodic table tells us the element's state. You don't need to worry about synthetic down here. Synthetic isn't a state. Synthetic just means that the chemical was made in a laboratory. It's not something you would find on Earth naturally. So we have solids, liquids, and gases. Now, how do you know that? Well, it's based on the color. So let me share with you. Of course, I closed it. Hold on. I closed it. Let me open up my periodic table again. Let me share with you that data booklet and show you, or I shouldn't say, or I should say remind you of this. We did this in chapter 4. I don't know if you guys can remember back then, but all right. So I got my data booklet open. Just give me 1 second and I'll share it with you. All right, share. I'm talking to myself, don't mind me. It's been a long week. I'm sure you guys feel the same. All right. So you should be able to see now my data booklet. And on the booklet, we have 3 distinct colors. Again, you can forget about synthetic. That's not a state. That's just a man-made chemical, or human-made chemical, I should say. So up top in the legend, I'm just kind of clearing up my circle here. We have 3 phases. Anything that's white, like boron, carbon, zinc, copper, iron, basically the metals mostly are always solids. And I know that because the periodic table has them listed in white. Well, what about liquids? Well, there's only 2. Now, I should mention that the phases on this periodic table are at a certain pressure and temperature. So like if you change the temperature, some of these things might change. But this is, you know, we always kind of consider that we're at room temperature or 25 degrees Celsius or something like that. So the 2 liquid phases from the periodic table are mercury, that's a metal, and bromine, that's a nonmetal. And then finally, the gases on the periodic table are in whatever color this is. I don't know what color that is. Salmon? I don't know. But those would include the nonmetals like nitrogen, oxygen, fluorine, all of the noble gases, and of course, if we go to the left, hydrogen. All right, so if you're dealing with an element on the periodic table, you would use the colors that the elements are. All right, so now let's be real. It's often not the case that we're dealing with pure elements in the chemistry lab. We typically deal with aqueous solutions. Now, aqueous solutions are ionic compounds dissolved in water. So how do we know if an aqueous how do we know if an ionic compound, you know, like sodium chloride or something like that, is aqueous, or would it be a solid? Well, we use the solubility table. We did this in chapter 4, which I'll go over this again in a minute, but I'm going to kind of leave it here for a second. You guys should know how to use the solubility table. Okay, and again, I will do a practice problem in like 3 minutes or 2 minutes, and I'll remind you how to look at the solubility table. Okay, the last thing, and then we're going to do some practice problems, is what about, okay, sorry, let me backtrack. I've told you how to find the state of matter for an element. I've told you how to find the state of matter for an ionic compound. How do you find the state of matter for a molecule or covalent compound? You know, like H2O, CH4, NH3. These are all nonmetals. So remember, covalent means non-metal. And in particular, it means molecules or molecular. Well, for these, I would have to tell you the state. There's nothing in our data booklet that has this information. So typically, if I was doing this, like myself, I would use the internet or a good data booklet in the chemistry lab. We have lots of books that tell us the states of these matters. So if I give you a non-metal covalent compound, I would have to tell you if it's solid, liquid, gas. I mean, one exception there is I probably wouldn't have to tell you what water is at room temperature, right? Water at room temperature would definitely be a liquid, but other chemicals that you might not know, I would have to tell you. Okay, so here's an example on the bottom of this slide. And this is kind of a good practice example for a few reasons. This example covers things from chapter 3, chapter 4, and chapter 5. Like this is what, like wink, wink, wink. This is a really good question. Chlorine, so I'm reading the example. Sorry, I'm just reading this here. Chlorine reacts with ammonium bromide to produce bromine and ammonium chloride. And then what I would ask you guys to do is convert the English words to a chemical equation. So how do we do it? Well, first, you have to do your naming from chapter 3. So step number 1, I know that chlorine and bromine as elements are what we would call diatomic. I don't know if you guys remember that from chapter 3, but we certainly did that. Chlorine naturally is Cl2. Bromine naturally is Br2. So chlorine, oh, sorry, I didn't mean to circle bromide. Bromine is Br2. So those are pretty easy. Then I get ammonium bromide. Ammonium is NH4 plus. It's on your periodic table under your polyatomic ions, or I should say it's in your data booklet under polyatomic ions. Okay, and ammonium chloride, NH4 and Cl minus. All right, so that's review from chapter 3. We would put these together then and get all of these formulas or chemical formulas on the bottom. Next part, we move into chapter 4. Chapter 4 is the chapter that tells us the phases of these ionic compounds. So chlorine and bromine, chlorine is a gas, bromine is a liquid. How did I know that? Well, go to my old friend, the periodic table. Chlorine is a liquid, bromine is a, sorry, I said that backwards. Chlorine is a gas, bromine is a liquid. I can tell because of the colors on the periodic table. All right, what about the other chemicals? I had ammonium bromide and ammonium chloride. So go up to your solubility table. Sorry guys, computer is a bit slow here. Scrolling through, here's my solubility table. I love this table. And I'm dealing with chlorine and bromine. So I'm up here, if you can follow my red pen, chlorine and bromine. So I go down that column. Most chemicals that are bonded to chlorine or bromine are soluble. Most chemicals are soluble when bonded to chlorine and bromine, except, oh, there's a lot of them. Chromium, copper, not mercury, silver, gold, mercury, lead, and then these compounds down here. None of those compounds are NH4. Ammonium or NH4 would be obviously in the most category. So both of these chemicals are soluble. So we would write next to them AQ. So that brings me back here. AQ, AQ, there we go. The part of this that is relevant for chapter 5 is between every element or every compound, we add a plus sign and we put an arrow to separate the reactions and products, or reactants and products. All right, we don't have much more for today, guys. There's only two more things I want to, well, one more topic I want to explain after this, but I do have two more examples for you. All right, write chemical equations for these compounds. One thing, I'm just going to change this to hydrogen. Oops. I'm just going to change the wording here so we can do it. Sulfite. Okay, hydrogen sulfite. All right, let's look at these questions. Sodium carbonate, so that's obviously ionic, reacts with sodium oxide, also ionic. I know it's ionic because it has a metal and a non-metal, to produce carbon dioxide. This is a molecule. Now, carbon dioxide, if this was on a test or final exam, I would have to tell you the phase of this. But realistically, especially for any of my students in here that are doing biology, you should know the formula for not the formula, you should know the formula, but you should know that carbon dioxide is a gas. And I mentioned that my biology students should know that because in biology, you talk about CO2 a lot. It's something that we breathe out in the respiration process. So we breathe in oxygen, gas, we breathe out carbon dioxide gas. But because this is a molecule, if this was a final exam, I would tell you that it's a gas because again, molecules, they can be solid, liquid, gas. There's no real rule here besides the intermolecular forces. Okay, before I get down to the next, or before we look at the answer, let's go down to the next one. Sulfur dioxide gas, this is a molecule. Reacts with water. Now, water is obviously a molecule, but you guys should know the phase of water. Water is one of the only chemicals where I probably wouldn't tell you if it's a solid, liquid, or gas, because every one of you, please, I hope every one of you would know that water is a gas at room temperature. Or sorry, water is a liquid at room temperature. Sorry, I'm trying to like think different things and say different things at the same time. So my brain is kind of breaking. So sulfur dioxide is a molecule, and I'm telling you it's a gas. It's reacting with water. We always assume we're at room temperature. So water would be a liquid, and I would produce the chemical hydrogen sulfite, which is ionic. So we would need our solubility table for this. Okay, now, if any of you guys have your notes printed, or you're following along on the PowerPoint, like from the D2L, you could probably see the answers, right? Here they are, but I'll pretend they don't exist. what I would like to do, I'm only going to give you a minute or two because again, the answers are here. But for those of you who don't have your notes printed and don't have the answers, why don't we take 2 minutes to predict or try to write these chemical equations? And then I just have, I'll need 10 minutes maximum to finish the last topic. So I'll give you guys 2 minutes to think about these. Again, if you have the answers in front of you, you can maybe just double check, see if I'm correct when I wrote aqueous or solid or something. So I'll be back in 2 minutes. We'll do the answers, and there's one more very short topic I'll introduce. So I'll see you in 2 minutes. All right, let's check your answers here. Now, again, I understand this is a little silly because the PowerPoint, the printing of the PowerPoint does have the answers there, but let's see this. Let's, check our work, make sure that I'm right or you're right. So, all right, let me erase some of this text here so we can kind of get a clear representation of these guys. Okay, so sodium carbonate, ionic compound, and I have sodium oxide, another ionic compound. Let's look at our lovely data booklet here. Let's see if we're right. So we have sodium carbonate, and we have sodium oxide. So for sodium carbonate, go down from your anion, the carbonate, and soluble chemicals here are hydrogen, sodium, potassium, blah, blah, blah. We can stop once we've seen sodium. So sodium carbonate would be aqueous. Na2O, sodium oxide, well, if you go down from oxides, none of these are soluble. They are all insoluble. So this would be solid. Okay, cool. So that's it. And then, sorry, let me go back to my notes here. We write the ionic formula, aqueous, arrow. So sodium carbonate reacts to produce sodium oxide and carbon dioxide gas. There we go. All right, let's see the other one. Sulfur dioxide gas reacts with water. So this reacts with means we add to it water. Water is a pure liquid to produce hydrogen sulfide, ionic compound. We look up sulfite and we would see that it is aqueous. So there you go. We're basically taking English sentences and turning them into chemical equations. Now, it might not feel like it, but writing chemical equations is faster than writing a sentence like this that I'm circling up top. It might not feel like it now, but when you practice this and you know how to name things and you can look up states really quickly, writing a chemical reaction is much quicker. It's just an easier way to represent a chemical reaction. So the finale of today, and I didn't get very far with this today, so I'll need basically two more slides, and then we're finished for today. Two and a half slides. Okay, so there's one piece missing from our chemical equations, one important piece. And if any of you have done chemistry before, you might have heard of this. It's called balancing equations. Okay, now I'm going to explain to you first, why do we balance equations, and then, what is it? So there is a law in science, right? There's many laws, but there's a law in particular called the law of conservation of mass. And the law states that mass in the universe cannot be created or destroyed. So what I mean is, if you The atoms that are there at the beginning of a chemical reaction will equal the atoms of the chemicals that are there at the end of the chemical reaction. By a chemical reaction, it is impossible for us to eliminate any atoms. And I mean, that's the law of the universe. You could break something, burn something, you could blow it up with dynamite, and the atoms are still going to be there. They might be different, they might look different, we can have chemical reactions change them, but they're still going to be there. So what that means for a chemical reaction is that the mass of the reactants will always exactly equal, and I mean exactly equal, the mass of the products. The only time that you would feel that this wasn't happening, I've seen it before, students do an experiment and they weigh it at the beginning and then they weigh it at the end, and they might notice that the masses are different. That's because you might spill some might be stuck to like your stirring rod or temperature probe. Often chemical reactions produce gas, and the gas might escape into the room, but all of those atoms are still there. Even if they might not be in your beaker, they're still in the room, they're still in the universe. So what it means for a chemical equation is, if you had 4 carbon atoms in the reactants, you have to have 4 carbons in the products. So I'm going to explain this. We're going to do an example, and then that's it for today. One thing before we get into that example, this is probably better for you guys to do, not for me to show you. This is a kind of like an interactive demonstration of how we can balance chemical reactions by using coefficients. I'll explain what that is in the next slide. So if you're bored today or tomorrow or before next class, you can try, go to this website. Now, you can type in the link in your web browser. You could go to my D2L and open the PowerPoint itself and then click on the link. Or what you could probably do is just type into Google this word here, or these words, fhetcolorado.edu, and then you could type in maybe balancing chemical equations. I think that will help. It's not homework, you don't have to do it, but it's kind of a fun little interactive demonstration of balancing chemical equations using little balances here. So I recommend, if you're bored, to check that out. But for us, we're going to do it the old-fashioned way on a piece of paper. Okay, so to balance a chemical equation, you have to make sure all of the atoms are equal in the products and the reactants. So in simple words, the number of atoms on the left have to equal the number of atoms on the right. That's the law, right? There's no changing this. One thing I should mention that isn't really written here is, to balance an equation, to make sure that we follow the law of conservation of mass, you can only change the coefficients. Used to be a good speller back in the day. I'll explain what coefficients are in a second. So you can only change the coefficients to balance a chemical equation. Now, what is a coefficient? A coefficient is a number in front of the chemicals. In front of is key. So it's a number in front of the chemical. So what I'm saying here is, and let me give you an example of like the worst thing you could do ever on a balancing equation. This is the worst thing you could do. Like, this would give me nightmares. You'd keep me up all night if you did this on a test or final exam or something. Okay, so like I'll show you. Let's just talk about this first. So look at the elements. Split the reaction in half. We have left, we have right. On the left, we have 1 sodium and 2 chlorines. I know I have 2 chlorines because of that number 2. On the right, however, we have 1 sodium and 1 chlorine. And this is the nightmare answer that students have given me, right? I've been teaching for 10, 11, 12 years. I don't even know anymore, but I've seen this. So what I've seen is a student says, okay, we have a problem. We have chlorine not being balanced. So I'm going to put a 2 here and I'm done. You cannot do that. There is no such chemical as NaCl2. NaCl2 does not exist. That it doesn't make any sense. Sodium is 1 plus, chlorine is 1 minus. They can only have a 1-to-1 ratio. So you cannot change the subscripts. You cannot change the subscripts. Okay? You can only change the numbers in front. Okay, so what does that mean? Well, luckily for you guys, we have little blank spaces here. And these blank spaces are where you'll put the balancing, or where you'll put the numbers. Okay, so let's have a look at this. 2 chlorines on the left, 1 chlorine on the right. So what I'm going to do is I'm going to put a 2 here. And okay, every time that you add a coefficient, take a step back, look at the equation, and re-examine everything. Okay, so every time you add a coefficient, you then want to re-examine everything. So now I'm going to erase these numbers. Now I have 2 sodiums and 2 chlorines. So I've created another problem. Now my sodiums aren't balanced. So I'll put another 2 here, re-examine my equation. And now I have 2 sodiums on the left, 2 sodiums on the right, 2 chlorines on the left, 2 chlorines on the right. We have satisfied the law of conservation of atoms. We are breaking the universe's rules. There we go. That's how you balance a chemical equation. So guys, I am done, but I want to explain something to you before we go on. There are 4 practice problems that I would love for you guys to try. So slides 19, slides 20, for next class. Now, it's not homework, it's not an assignment. You don't have a quiz this weekend. You can kind of relax here this weekend. So you don't have labs or anything this weekend. You do have labs next week, but you don't have anything this weekend. So you should try these problems. And then on Monday's class, we'll look at the answers. It's like solving a puzzle, but I will warn you that balancing can be tricky. It can be frustrating sometimes trying to get that puzzle to work. The challenge of the puzzle is for you guys to make the elements on the left equal the elements on the right. So every atom needs to be the same. And the only way to solve this puzzle is to put numbers in front of the elements. You cannot do anything else. Don't change my numbers down here. So you can't change this number or this number or this number. They have to stay the same. All right, guys, so that's it for me. I'm going to hit stop record. If you have any questions, let me know. Other than that, have a fantastic, wonderful, and safe weekend. And I will see you next week. Labs next week are on campus. So lab number 9 is on campus. Lab number 10 is also on campus. So the 2 labs you have remaining, you must come to school for those. Lab 9 is next week. All right, so I'm going to hit stop recording and answer any questions you guys might have.